Okay, class, welcome back. Today we are going to continue our discussion on gas laws with the ideal gas law. My goal for today is that we'll be able to manipulate and use the ideal gas law to solve for pressure, volume, temperature, molar volume, molar mass, and density. With saying all that, let's dive into all that math that's going to go along with these ideal gas laws. In our previous lecture, we have discussed the three simple gas laws. Boyle's law has showed us that volume and pressure are inversely proportional. Charles's law tells us that volume and temperature are directly proportional, while Avogadro's law tells us that the volume of the gas and the number of moles it occupies is directly proportional to each other. If we combined all three laws together, we would get volume is proportional to the number of moles of that gas times the temperature of the gas, all divided by the pressure of the gas. If we want to replace the proportionality sign with the equal sign, then we're going to have to incorporate a proportionality constant. The ideal gas constant that we are going to plug into this equation is going to be R. So our equation should now read volume equals ideal gas constant times moles times temperature over pressure. If we rearrange this equation, we get the ideal gas law of PV equals nRT, or pressure times volume equals moles times ideal gas constant times temperature. The numerical value for our ideal gas constant is always going to be 0.08206 liters times atmosphere over moles times Kelvin. When working ideal gas problems, because there are so many components to it, it is imperative that we use appropriate units. For ideal gas law equations to work, pressure must always be in atmosphere, volume must always be in liters, moles needs to be in moles, temperature also has to be in Kelvin. If any of these units are not an appropriate unit, we must first convert them before we even plug them into the ideal gas law equation. Okay, so now we got that out of the way, we can start working an ideal gas law problem so that you can see how these work. Here's the problem. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 degrees Kelvin. I would first start working this problem by writing out my initial gas law equation, so PV equals nRT. After that, I would write out all my knowns, so R is a constant, so I would write down 0.08206 liter atmospheres per mole Kelvin. Next, I would write down what is given to me in the word problem, so moles are given, we have 0.845 moles. Our pressure is also given in atmospheres, so 1.37 atmospheres, and our temperature is given in Kelvin, so 315 degrees Kelvin. Because all these are appropriate units, we can now move on to our next step. We are asked to solve for volume of the gas, so we need to rearrange this equation so that volume is isolated by itself. This is easy considering all we have to do is divide both sides by pressure. This gives us a new equation of volume equals moles times ideal gas constant times temperature, all that divided by pressure. Now my last step is to plug into the equation, so I should read V equals 0.845 moles times 0.08206 liter atmospheres over moles Kelvin multiplied by 315 Kelvin. All this is going to be divided by 1.37 atmospheres, or the pressure. Once I plug all these in, do the math, calculate it out, our gas is going to occupy 15.9 liters. Let's work another one. This time, let's calculate the number of moles of gas is present in a 3.24 liter basketball inflated at a total pressure of 24.3 psi at 25 degrees Celsius. First, let's write down our equation and what we know. So PV equals nRT, and we have pressure is 24.3 psi, our volume is 3.24 liters, and our temperature is 25 degrees Celsius. Before we go any farther, we must convert our pressure and temperature to appropriate units. So let's convert 24.3 psi into atmospheres. We do this by multiplying it by 1 atmosphere over 14.37 psi. Once I multiply and divide out, I get 1.6531 atmospheres. Now that we got that taken care of, let's do temperature. To convert from Celsius to Kelvin, all I have to do is add 273.15 to my Celsius reading. So my temperature should read 293.15 degrees Kelvin. Now that I have everything in appropriate units, we can start plugging in and solving for this problem. We are asked to solve for the number of moles. So we need to rearrange our ideal gas laws so that we get moles isolated by itself. In order to do this, I am going to have to divide both sides by RT. Now I have PV divided by RT equals moles. Now that I have all this done, we just plug in our knowns, so the equation should read 1.6531 atmospheres times 3.24 liters over 0.08206 liter atmospheres divided by moles Kelvin multiplied by 298.15 degrees Kelvin. Once we do the math, we get 0.219 moles as our answer. Okay, so we just explained how to use the ideal gas law to calculate one of the variables of pressure, volume, temperature, or moles, and if you are given the other three. Now we're going to turn to three other applications of the gas law: molar volume, density, and molar mass. The volume occupied by 1 mole of a substance is the molar volume. For gas, we often specify molar volume under a condition known as standard temperature and pressure, also known as STP. Standard temperature is 273 degrees Kelvin, and standard pressure is 1 atmosphere. Using the ideal gas law, we can determine the molar volume of a gas. This is simply done by rearranging the ideal gas law equation. Our rearranged equation should read volume equals nRT over P. If we sub our STP pressure and temperature into the equation for 1 mole of a substance, we would get a standard gas volume of 22.4 liters. We can use ideal gas laws in combination with mass measurements to calculate the molar mass of an unknown gas. All we have to do is rearrange the equation so that we can solve for the number of moles like we did earlier, so N equals PV over RT. Once we solve for the number of moles a gas has, all we have to do is use our mass given and divide it by the moles we calculated. This would give us our molar mass. If I have a sample of gas that has a mass of 0.311 grams and its volume is 0.22 liters at a temperature of 328 degrees Kelvin and a pressure of 1.1658 atmospheres, and I want to calculate the molar mass of this gas, I would first need to solve for the number of moles present within the gas. This means I would solve the equation N equals PV over RT. We would plug in our given values of 1.1658 atmospheres times 0.22 liters divided by 0.08206 times 328 Kelvin. Once I did this, I would have 9.53 times 10 to the negative third moles of this gas. To find the molar mass, all I have to do is take my mass given, which is 0.311 grams, and divide it by 9.53 times 10 to the negative third moles, or how many moles I calculated, and I would get that this unknown gas's molar mass is 32.64 grams per mole. The last thing we're going to talk about with gases today is how to determine the density of a gas. We can calculate the density of a gas under conditions by using the ideal gas law. To do this, we're going to rearrange the gas law so that we can get moles over volume equals pressure over R times T. Since the left side of the equation is moles per liter, or moles over volume, we can change that to molar density. If we multiply our molar mass by our molar density, we would get the density of our gas in grams per liter instead of moles per liter. So our finalized density equation would be density equals pressure times molar mass over R times temperature. So let's work a practice problem. Calculate the density of nitrogen gas at a temperature of 398 degrees Kelvin and a pressure of 0.993 atmospheres. So we know our equation is density equals pressure times molar mass over R times T, or temperature. So all we're going to have to do is find our molar mass of nitrogen, then we can plug that in. Nitrogen's molar mass is 14 grams per mole, but it is diatomic and it is found as N2 when it is not bound to anything. That means we're going to have to double our molar mass. So our new molar mass is 28 grams per mole. Now we just plug everything into the equation and we get our density equals 0.993 atmospheres multiplied by 28 grams per mole over 0.08206 liter atmospheres over moles Kelvin times 398 Kelvin. Once I do my calculations, I get a density of 0.851 grams per liter. Okay, y'all, that's enough math for today. We can use the ideal gas law to do many different calculations, whether it's to find pressure, volume, temperature, or a more obscure unit like density or molar mass. I hope this video helped you out, and keep up the good work in class. See you next time.